So with our valence electrons, go back to here. So valence electrons are the electrons on the outermost energy level. And these are important because they're on the outside. They're in the highest energy level. And it's important to talk about the electrons on the outside of an atom because they're the things that do the interacting. So like, it's not the inner atoms that do the interacting, it's the outer atoms that do all the interacting, that interact with other atoms, that do bonding and stuff. So looking at this silicon electron configuration, I've highlighted the valence electrons for you. But notice how I can tell this. I have three different energy levels. I have 1, 2, and 3. What is the highest energy level available? 3. How many electrons are in the 3 total? 2 here, 2 here, 4 valence electrons. So it's just count up the total in the highest available energy level. What if I have something that has like a 3D in the middle? Well, that 3 is not valence because it is not the highest level. The highest level you can see here is 4. So I have 6 valence electrons because of that. But here's a trick. Your valence and your periodic table go together. So everybody in group 1 has a valence of 1. Everybody in group 2 has a valence of 2. And then we skip that valley, the transition metals, valence of 3, valence of 4, valence of 5, valence of 6, valence of 7, and valence of 8, except helium only has 2. But you can just kind of count your tall groups across 1 through 8, and then get your valence. You don't have to actually look at electron configurations to do that. So I highly recommend doing that. It's a lot easier. And valence are important because they tell us how things are going to bond. When we talk about bonding in chapter 6, then this is going to be very important. So you can kind of see some of these valence configurations here as you move across. Like everybody here has 7, everybody here has 8, everybody here has 2. You can see that in practice. We're going to talk about Lewis symbols a little bit more in chapter 6, but they're just, you put dots for valence electrons, that's it. And you put 1 dot on each side of the element symbol. So if your homework is asking you for this, great. If not, I'm not going to put this on a test or a quiz for chapter 4. We'll revisit this again. This same table in chapter 4 we'll revisit in chapter 6. But you can kind of see how I put together these dots as I move across. And our last topic for this chapter is periodic trends. So we're going to define the trend, and then I'm going to tell you about it. So atomic size, aka atomic radius, is defined as the distance between the nucleus and the outermost electron, which is called what kind of electron? The valence electron, yeah. Okay, so what's happening? This kind of looks like a snowman, right? So I think about, building a snowman and then knocking the snowman down. That could be helpful in helping you remember this trend. But as you move down the periodic table, we get bigger. Because think about a Bohr model. As you move down the periodic table, you're adding energy levels. So I can literally draw getting bigger. Right? So as I move down, I get bigger just because there's more energy levels. So that's why I get bigger. But look at what happens as I move across, like from lithium to fluorine. I get smaller. Why do you think that is? It's kind of a hard question, but see if you can give me a guess. So as I move across the periodic table, I have the same energy. So I'm all, energy level 2. But let's look at our protons. So there's 3 protons and 3 electrons, so 3 plus, 3 minus, 4 plus, and 4 minus. And over here is 9 plus and 9 minus. So what do you think the level of attraction is going to be like? 9 plus and 9 minus versus 3 plus and 3 minus. So fluorine has what kind of attraction compared to lithium? Fluorine electrons and protons have a greater attraction. And what do you do to something you're more attracted to? Pull it closer, right? So we're holding it closer because there's an increased attraction between the two. But just knowing the trend decreases across and increases down is good enough. So we're also going to think about something called ionization energy, and it relies on the size trend. So ionization energy is the energy required to remove an electron. So if you think about lithium compared to potassium, this is a positive nucleus and this is a negative electron. So what do they do with each other? Right, they attract. So if I want to pull away this negative and the nucleus is right there, it's going to be hard to pull it away, right? So it's difficult to remove. Remove the negative if the positive is close. But if I look at potassium, they're farther apart. It's easier to remove if they're farther apart. Like if something that I am attracted to is like way far away from me, it's easier to remove. If I leave my iPad like downstairs in the lobby, it's easy to remove from me. But if I'm holding it close to my chest, it's harder to remove. That's all this is. Okay. And then your last trend you need to know right now is called metallic character. And this is super obvious. More metal is more metallic. So who's the most metal? Whoever is at the bottom left. So francium is the most metal. And then up here you can think about fluorine. And I don't really use the noble gases in these because they're kind of separate from everybody else. They're special. They don't interact. So I would think fluorine is the most non-metal. And they're kind of easy to remember because they're both Fs and on opposite sides of the periodic table. So metallic character, if you go more towards the metal side, the left side and down, you get, more metallic. And then a nice little table here for you.